Hi, this is Mrs. Clark, and welcome to my video on geometric sequences. First, take your foldable, and on the outside cover, let's write together just a little description about geometric sequences. Geometric sequences are a pattern that is multiplying by a common number to get to the next term. So this is a different type of sequence than most of the ones that we've looked at so far. So go ahead and write that down on the outside cover of your foldable. Just like we learned the explicit rule for arithmetic sequences, we're now going to be looking more closely at geometric sequences and learning how to write an explicit rule for those. It's important that you make sure you're writing down everything onto your note sheet as you're watching the video, listening to the explanations, and pausing whenever you need to catch up because I'm going too fast. First, we have our recursive rule. So because we're looking at a different kind of explicit rule for a different kind of sequence, it's going to look similar but different at the same time. So our recursive rule starts the same as it did for arithmetic sequences. A sub n equals A sub n minus 1. But this time, since we don't have a common difference, we have a common ratio, and ratios are numbers that involve multiplication. The next step is going to be times, so I'm going to use a dot to represent times, r, and r again is our common ratio. So our recursive rule says if I want to find one term, I need the previous term times the common ratio in order to get it. When we look at the explicit rule, it allows us to fill in the rule for any term in our sequence, and we can figure out what that term would be. So I don't have to know any particular term, but in the recursive rule, I need to know the previous term. So explicit rule sometimes is a little bit more helpful because it allows us to just get any term anywhere in the sequence. So the explicit rule starts again the same as it did for arithmetic. A sub n equals. This time, we're going to start with our first term, which is a sub 1, multiply that by the common ratio, and we do have the n minus 1 in here, but this time our n minus 1 is an exponent. So I'm going to put it up here above the r, so it's r being raised to the n minus 1 power. You may want to make yourself a note here, pointing to this, reminding yourself that it's an exponent. If you don't write your notation very clearly, you may think that you're distributing an r through a parenthesis to n minus 1, but in fact it's being raised to that power. So much like in the arithmetic rule, n is still the number of the term that you're trying to find, and we have a sub n, which is the term in the sequence you're looking for, and a sub 1 is the same as it was before. A sub 1 is still the first term in the sequence. And r, as we discussed earlier, is the common ratio. So fill all of those in and pause the video if you need more time. Now we're going to find the explicit rule given the example at the bottom, 2, 6, 18. So if I want to write the explicit rule, first thing I need to know is what is the common ratio. So again, looking at these numbers, we used this one as one of the examples earlier. 2 times 2 times 3 gives us 6. So if I want to find the common ratio, as long as that continues for the others, then 3 will be my common ratio. 6 times 3 also gives me 18. So my common ratio is 3. So to write my explicit rule, I'm going to start with that a sub n equals. I need to know my first term in the sequence. Well, that is 2. So this number here is my first term. So I'm going to start with that, 2. And then I have a multiplication symbol. Then I have an r, so my r is 3. And then I need to raise it to the n minus 1 power. So unlike the explicit rule for arithmetic, I had to distribute and simplify. There's no distributing or simplifying here. This is as simple as I can make it for right now. So a sub n equals 2 times 3 to the n minus 1 power. But when I go down to the bottom and do the example to find the sixth term, I'm going to replace my n's with 6. So I'm really going to be finding a sub 6 equals 2 times 3 to the 6 minus 1 power. So if I remember back to my days of learning PEMDAS, the first thing I need to do is my parentheses. So I need to reduce the parentheses, which is 6 minus 1. I need to just bring that down to a 5. I'm going to get us some more room. Let me rewrite that for us. A sub n equals 2 times 3 to the 6 minus 1 power. So if doing my PEMDAS, first my parentheses, I'm going to do a sub n equals 2 times 3 to the 5th power, because 6 minus 1 is 5. You can leave the parentheses there or not, but now they're cleaned up to one number, so I don't necessarily need them, so maybe I'll just write 3 to the 5th power. Next thing in PEMDAS is my exponents. So now I have to get rid of this exponent of a 5. So in my calculator, I need to do 3 to the 5th power. You have your phone. Let me show you how to do that on your phone. All right, so if I want to use my phone calculator to do 3 to the 5th power, what you need to do is turn it to the side so you get the extra options. And first thing we're going to do is press the 3. And then we need this button over here that says x to the y power. That's going to let me raise it to another power. And I'm going to hit 5 because I want 3 to the 5th power. And I'm going to hit enter. And we get 243. So that means 3 times 3 times 3 times 3 times 3 is 243. So again, use that x to the y power to help you do that. So back to what we were writing. We know that we have a sub n equals 2 times 243. We just did that in our calculator. And then we can go back to our calculator, and now we're going to finish our PEMDAS. Multiplication, division, addition, subtraction. All I have left is multiplication, and then I'll be done. So we're going to do my multiplication. A sub n equals 2 times 243, so we get 486. So our sixth term is 486. So fill that all in on that bottom of that green paper. If you need to go around the side or whatever because there's not enough room, feel free to definitely do that as well. Then we're going to go on to the other side of the worksheet and do the example about the tennis tournament. So pause it if you need more time to write it down. Otherwise, in the Wimbledon tennis tournament, 128 players begin in round 1. After each round, half of the players are eliminated. So we need to fill in this table based on the information given to us. So in round 1, they told us that we had 128 players. In round 2, they said we have half of the players because half of those players are eliminated. So half of 128 is 64. So round 2 gets 64. Round 3, half of 64 is 32. Round 4, half of 32 is 16. Round 5, half of 16 is 8. And then we're going to leave the last one, n, and a sub n. To remember that n represents the round number, and a sub n represents the number of players in that round. So next we have to write our recursive rule and our explicit rule. So we need to know what's happening from term to term as I go down the sequence of players. If I'm looking at the players, I definitely can see that they're decreasing from 128 down to 64, 64 down to 32. We were taking half each time. We were dividing it by 2. But if you remember, the common ratio needs to be written as a number that we can multiply. So if we're taking half, that means we're multiplying by half. Each time we're doing a half, a half, a half, and a half. And we can keep going forever and ever. Our table just happens to stop at number 5. So to write our recursive rule, I need to start with my a sub n equals a sub n minus 1. So the term I want equals the previous term times the common ratio, and the common ratio we just figured out was a half, because each time the number of players was being cut in half, dividing by 2, which we said we would write as a half. So that's it for recursive rule. When we go to do the explicit rule, we're going to start again, a sub n equals, but this time we need our first term. The first term in our sequence of players is 128, so we're going to start with that, times the common ratio, which we know is a half, raised to the n minus 1 power. And there's no simplifying to do with explicit rule, so we're going to leave that as it is, and then we're going to move to the bottom and graph this data. So filling in the scale for both the round and the players can be kind of tricky. Our rounds, we only really go up to 5 in our table, even though we can continue that on. So I'm going to spread them out a little bit more. It's hard to see the lines, but pretty much I look at the first box, and I'm going to skip that and go to the second box and mark number 1. So that's the first round. Then I'm going to skip the third box, go to the fourth box, and mark it 2. Skip, and then mark it 3. Skip, 4. Skip, 5. I'm going to keep going. Skip 6, skip 7, skip 8. I like to fill it in all the way across. We can always continue the pattern even though our table stopped when we go to make our points. On the y-axis, I used every box as 10 because the biggest number we have is 128, so I need to be able to get to 130. So I did 10, 20, 30, 40, 50, do this with me, 60, 70, 80, 90, 100, 110, 120, 130. All right, so our first number in our table for round 1, we have 128. So I'm going to go to 1 on the round up to 128, and I'm going to make a point and approximate it as best I can. It's going to be a point closer to 130 than to 120. And I'm going to do that for each round in the table. So the next round 2 is 64. So I'm going to go from 2 up to about 64, which is almost halfway between 60 and 70, and make a dot. Then I'm going to go from 3 to 32, so it's a little bit above 30, closer to 30 than 40, and make a dot. Your dots are going to be a little more precise because I'm trying to make it on the iPad, which isn't so easy with my finger. Number 4, I'm going to go up to 16, so a little bit more than halfway between 10 and 20. Number 5, I'm going to go up to 8, which is just below 10. And then I can continue. I know 6 is going to be 4. And then I know 7 is going to be 2, 8 is going to be 1. So if I go to make connect them and sort of sketch a connection, it's definitely not a straight line. Oops. If you notice, it's curving around and getting smaller, 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 smaller. So I'm sure you've seen graphs like this before. This is not like the graph that we did for arithmetic, because the arithmetic graph was a straight line. This is not a straight line. It's more of a curve. There we go. That's better. All right. And this would continue off to the right. So I'm going to put an arrow on the right. All right. So there you go. There's our notes on the explicit rule. You can rewind anything or write down any questions that you have. I'm going to practice the explicit rule with some geometric sequences, the same way we did with arithmetic sequences. So I will make a separate video for that. Thank you.